Flying by ML. I'm Van Warren, and this is my PhD dissertation proposal defense. I'm going to introduce 4 innovations to you today. The first is that a simple change in viewpoint provides a large complexity reduction. The second innovation is that the trained test data can be generated from a single keyframe. The third innovation is functioning in the presence of 4 kinds of noise. The fourth innovation is artificial interpolation using a CNN. First, some definitions. CNN stands for Convolutional Neural Network. ML stands for Machine Learning. RL stands for Reinforcement Learning. VFR stands for Visual Flight Rules, the fair weather kinds of flying. IFR stands for Instrument Flight Rules, which is almost all weather kinds of flying. AC stands for Aircraft, and HW stands for Computing Hardware. Convolutional neural networks are fantastic and versatile creatures. I will explain how they work using MNIST, the hello world of CNNs. For further information, you may check these links for an overview, the mathematics, and a demo you can play with. For those of you online, the links are in the comments section below. Handwriting recognition using ML had its origins in the work of Yann LeCun and Karina Cortez of Google. They compared 64 CNN classifiers over the period from 1998 to 2008. If we take the 50 best classifiers, the mean test error drops to 1% with a standard deviation of 1%. In this work, I will extend CNNs to invert affine transformations, one example of which is rotation. To understand my extensions, it is helpful to understand how CNNs work in the first place. This page of code from a Python Jupyter notebook builds a 16-line MNIST CNN deep learning model. It runs in Google Colab, and you can quickly type it in and run it for free. There are 3 sections to this code. The first block of 3 lines is the import of essential TensorFlow libraries. The second block is the loading and shaping of the data into tensor forms suitable for training. The third block is the definition of the model and the fit function call which trains the model. The configuration arguments for the model are hyperparameters. I call them hyperams for short. Hyperams in ML are the result of a great deal of costly experimentation. Let's zoom into the details of the model. First, we declare a sequential model, which is a left-to-right ordering of the process pipeline carried out sequentially with backpropagation. Next, we add a 2D convolution layer that will create 32 feature maps representing idioms like loop and strokes in the case of handwritten digits. The feature map is created using a 3x3 convolution operator acting on an image of 28 by 28 pixels, 1 bit deep. Next, we append a dense, fully connected layer of 100 neurons using a nonlinear activation function called a rectified linear unit, or just ReLU for short. It has a response curve that reminds me of a semiconductor diode. There are other activation functions we could use, like sigmoid or hyperbolic tangent, but ReLU works very well. Our activation function needs to be differentiable so that backpropagation of the neuron weights can be computed. The output of the 100 neuron network is flattened into a 10 neuron final stage, which will use the softmax function to predict the digit. It is in this phase that my extension will occur. We then compile the model using the TensorFlow library, including options of sparse categorical cross-entropy with the Atom Adaptive Momentum Learning Optimizer and an accuracy metric so that we can track the learning curve. Finally, we train the model using a batch of 1000 and 1 epoch for brevity. A quick sidebar on activation functions. The ReLU can be implemented as a max function, which is both differentiable and very fast to execute. Despite its name, its job is to introduce nonlinearity into the machine learning process. Note the similarity to diode response curves, suggesting one could try using forward bias. The diode is the fundamental semiconductor device and appears in a neural context here. Why nonlinear activation functions? Because otherwise, many layers behave just like a single perceptron. This is because the summation of linear functions would otherwise just produce a linear result. Key change for a sea change. When there's a change of paradigm, everyone starts at 0. To demonstrate this extension of CNNs, a relevant example is required. We will use one from the domain of general aviation, applicable to autopilots and self-flying aircraft. There are several technical revolutions affecting aviation worth considering in this context. The first is the machine learning revolution, with which we're all familiar. The second, similarly, is the web, edge computing, and cloud revolution. There's also the autonomous self-driving vehicle revolution, and finally the drone revolution. Previously, there was a composite material revolution that made these electric aircraft possible. Earlier this year, I proposed using a CNN for a general aviation autopilot under VFR rules. This block diagram has 2 sections. The top section shows a video camera feeding a CNN, which outputs the current roll angle PID controller, implementing Laplace transform control laws to keep the wings level. The bottom section shows a video camera feeding a pre-trained model, which outputs the current roll angle to a reinforcement learning program. The goal was to compare and contrast the performance of conventional controllers to reinforcement learning controllers. My committee advised me to downscope my efforts, so I focused on the CNN. This led to some unexpected benefits. Innovation 1, VFR to IFR. When I first conceived of using ML as an autopilot for roll control, I planned to place the video sensor outside the aircraft. My plan was to train the CNN to recognize all kinds of flight attitudes, terrain, lighting conditions, and weather. This was going to require collecting extensive training footage that was general enough to represent all the combinations that might be encountered. Now imagine that you're flying by the side of a mountain and the video sensor thinks the incline of the mountainside represents level ground. This is a problem, the solution to which illuminates an important robotic principle. Though simple to state in retrospect, it may be the most important step that was made. It turns out that by directly imaging the dial face of a gyroscopically driven instrument, 3 important problems were solved. First of all, there was a vast reduction in visual and computational complexity. Secondly, a solution was obtained that was applicable to almost all weather flight. The third good thing that happened was that it was no longer necessary to tamper with expensive aircraft instrumentation. And so emerges the general principle that specialized sensing devices reduce the ML workload and hardware requirements. Amplifying this point further, robotic sensing imitates the biological. We could sense with our vision, but this would create a large and distracting cognitive overload. Instead, we determine our geometric attitude with a specialized sensor, which in the human are called the semicircular canals, one for each axis of roll, pitch, and yaw. We were made to fly. Consider the standard 6-pack of general aviation. The CNN sensing techniques described here are applicable to all these standard instruments. We will start with roll axis sensing, which is provided by the bank indicator, part of a dual instrument called a turn and bank indicator. Even in modern automated cockpits, these basic instruments persist. Let's focus on the bank indicator component, which performs roll sensing in the turn and bank indicator. Some image processing is necessary to prepare the data for the CNN. We start with a 1036 by 1036 RGB image of 3.2 megabytes in size. The first thing we do is crop and reduce the image to 600 by 600 RGB pixels. Next, the contrast of the image is enhanced. Now the turn coordinator is clipped out, leaving just the bank indicator. Now we have an important decision. Should our robot see in color, grayscale, or black and white? Grayscale was chosen since the image edges alias as they rotate. Grayscale and bicubic sampling preserve edge pixel values, improving the visual acuity of the CNN. Then we crop further to make the glyph of the instrument symmetric. A problem arises. As the clipped glyph rotates, part of the wing is missing. The solution is that we rotate before the previous clip when building the train and test set. The second innovation is that the train and test sets can be generated by the forward-affine transform of a single keyframe. One thing we notice when doing this image processing is that CNNs have incredible visual acuity. In the absence of noise, which we will add in a moment, the CNN tolerates an image reduction factor of 22. That is, a 22-fold reduction in the amount of information that the CNN must process, so it can run faster and requires 22-fold fewer neurons in each of the deep layers. Here is the standard K-fold cross-validation during training that shows the loss and accuracy functions as well as the area under the curve of the receiver operating characteristic. It is an interesting statistical device that dates back to the invention of radar in World War II. But I digress. Innovation 3, functioning in the presence of noise. The next innovation is to make this work in real-world conditions that include 4 kinds of noise. 4 kinds of noise are currently addressed. Fine-grained sensor noise that come from the camera's CCD itself, coarse-grained lighting noise, which comes from varying illumination conditions within the cockpit, camera offset noise, which is a translational affine operation, and camera zoom, which is an affine scaling operation. Innovation number 4. The next innovation is that we can do artificial interpolation with a CNN to invert the affine transformation that indicates the aircraft's roll angle. This is the most mathematically interesting innovation for me personally, and probably the one with the broadest applicability. It is called artificial because we interpolate categories of related objects to produce a numerical rather than categorical result. Now for a quick sidebar on affine transformations. 4x4 matrix multiplies can rotate, scale, translate skew, and apply perspective to geometric points in 3-space and to pixels and images. They are the bread and butter of modern 3D computer graphics hardware and software. Entire companies have been built around making these operations fast, starting with Silicon Graphics and continuing with NVIDIA. This artificial interpolation is done by what I call a prediction vector trick. The CNN is adapted to recover the roll angle using the entire prediction vector. This inverts the usual process of affine transformation. It's analogous to the kernel trick in support vector machines. The kernel trick of SVM is to convert the dot product of the support vectors to the dot product of the mapping function. Now, we usually think of CNNs as giving categorical results: car, truck, airplane, or horse, zebra, dog, and cat. The CNN backend can be rewired to invert the affine transformation of rotation. We will also use it to invert scaling and translation when noise is introduced. Here's how it works. Instead of doing the argmax on the prediction vector and choosing the most likely thing that happened, we do a dot product between the bank angle array and the decision vector. So you can see here in the prediction vector there's 3 hot spots, and those 3 hot spots are going to contribute to our bank angle. We gather all the inferred angle fragments and then sum them up. So I have a few next steps in completing my work. The next step is to optimize the 16 hyperparameters. With 16 bounded cases and a midpoint, there are 43 million possible runs, just to characterize the space. Thus, grid-based search is not feasible. A deep dive is currently underway using Jason Brownlee's optimization opus as a starting point, with another innovation in the works: Administrivia. The remaining 5 slides enumerate next steps in completing the dissertation. Using Python Jupyter notebooks and Google Colab GPUs in the cloud is a paradigm shift in software development. Many lessons have been learned, but the remaining struggle is how to decompose large problems into manageable pieces while retaining good visibility into the software details. This slide shows the tension between having one monolithic notebook and several smaller notebooks to work the problem. Here we see the statistics for an MNIST run side by side with a roll indicator run. This duality has been maintained for safety and verifiability reasons. The most important time saver is splitting the train test image generation from the inferencing task. Image generation currently takes more time than training, but it only needs to be done once. This slide shows the size of 20 versions of the code developed during prototyping. Notebook size decreases as function libraries are factored out to external files. A later version, P, has 1,232 lines, a departure from the 18-line example we showed above. This is a lot given how terse and expressive Python is. This work required 189 references and multiple consultations to SAME. Every one of the aviation, technical, and development references were essential in constructing this proposal and software. The references accumulated during this work would make an interesting ML Python tutorial on their own. So that's it. Those are the 4 innovations for CNNs for affine inversion. Hope you enjoyed the talk. Please click like in the link below. Thanks a lot for watching.